So I will be talking on characterizations of Kerr-de Sitter in arbitrary dimensions from conformal infinity. This is a working collaboration with Mark Mars, and if during the seminar, and especially in the technical parts, any of you have questions, feel free to raise your hand or interrupt me. So let me start by giving some context and motivation, introducing some very general facts on Kerr and Kerr-de Sitter in 4 dimensions. So as you know, Kerr is a very important metric in physics because it's believed to represent the end state of pure gravitational collapse. But it is also privileged from a geometric point of view, as for example, it satisfies uniqueness results among stationary black holes with zero cosmological constant. And another important geometric property in this seminar is the so-called alignment of the Weil tensor with the stationary Killing field, which was proven by Mars in the early 2000s to characterize Kerr. These properties stated more precisely following way. So we call a vector field, and we find these two form F out of X, and the so-called self-dual Weil tensor. We say that the spacetime is aligned if these two tensors are proportional, where Q is a complex scalar function, and the STF means the trace-free part. Now, the Kerr-de Sitter metric was proposed by Carter in the 70s as a generalization of Kerr to a lambda positive universe. Both metrics share several properties, but it's worth to ask ourselves, in what sense is Kerr-de Sitter the generalization of Kerr? It would be optimal to have some uniqueness result also for Kerr-de Sitter, but no uniqueness theorem have been proven so far in the positive cosmological constant case. Unfortunately, Kerr-de Sitter happens to be also characterized by the alignment property. So there are several lambda positive vacuum families of metrics satisfying the alignment property, and this is what we call the Kerr-de Sitter-like class. Let me emphasize here, when I say a family, I mean a collection of metrics depending on a number of parameters, which all share the same essential properties. And when I say class, I mean a set of families which share one more general property. So in this case, is the alignment property. Okay. Now, all families in the Kerr-de Sitter-like class are explicit and have been completely classified by Mars and Zenovita. And they all have the important property of admitting a smooth conformal extension. So it's natural to ask ourselves, what are the asymptotic features of this Kerr-de Sitter-like class?
And there are solutions of Einstein equation?
Yes, they are all lambda vacuum.
All
lambda positive vacuum, yeah. In the lambda positive vacuum case, the conformal infinity stride is a privileged space-like hypersurface. And moreover, one can pose an asymptotic initial value problem, which is an initial value problem with data at conformal infinity, which happens to be well posed. So if we calculate the asymptotic data of the Kerr-de Sitter-like class, the alignment property is a very particular imprint in this data. The data consists of a Riemannian 3 manifold equipped with a traceless and transverse tensor or TT tensor. This is the Cotton tensor of gamma, is given by this expression. The psi is given by the similar expression with different constants, K1 and K2. And psi is the restriction of the aligned Killing vector field onto stride, and is a conformal Killing vector field of gamma. You don't need to remember the explicit form of this, but just try to keep in mind that this is a very simple set of data, which can be constructed only out of one conformal Killing vector field and one metric. Now, in higher dimensions, there is a generalization of Kerr-de Sitter proposed by Gibbons and collaborators. To obtain this metric, they assume the Kerr-Schild structure holding in 4 and higher dimensions too. For those who are not familiar, the Kerr-Schild structure is a decomposition into a background, the Sitter metric, plus this term. H is a function, and K is a null vector. Now, the explicit form of the metric is found by writing the Sitter in some cleverly chosen coordinates. The details of the metric, they are not important, just to show you that everything is explicit. All these functions are explicit functions, which are rational functions in this these coordinates. And this metric depends on one mass parameter and n-half integer part rotation parameters. So this can rotate in different around different axes with different speeds. So again, Gibbons extends Kerr-de Sitter to higher dimensions, and they both share a lot of properties. But is there any sense that we can say that Gibbons is the natural extension of Kerr-de Sitter metric, Kerr-de Sitter metric in some sense? We could try to look for some property, geometric property like the alignment property, but this needs a space-time dimension 4. So the first question we ask ourselves is, how can we obtain a characterization of Gibbons Kerr-de Sitter? And if we find this characterization, does such a characterization allow for a natural definition of Kerr-de Sitter-like class of the spacetimes, like the alignment property? So this is what I will try to answer in this seminar by looking at the asymptotic properties of these spacetimes. For that, I will have to discuss a little bit the asymptotic initial value problem in higher dimensions. So let's start by denoting M tilde D tilde and MG, n+1 Lorentzian manifolds. The space-time dimension is going to be n+1 always. And let omega be a smooth function defined on M. So we say that this triple MG omega is a conformal extension of M tilde D tilde. If there exists a conformal embedding from M tilde into M, which relates the metrics by the conformal relation. Omega restricted to the image of M tilde is strictly positive, and it is such that at the boundary of the image of M, which I shall denote with this character stripe, this is a non-empty hypersurface which coincides with the zero-level sets of omega, where its gradient is not zero. This is the very basic definition of conformal extension, and the picture is like this. So we have an original space-time M tilde D tilde, which we map inside a bigger space-time MG, to which we attach a boundary stripe, which represents the asymptotic region of M tilde D tilde. The conformal extensions are highly non-unique, so we are given a conformal extension, and we scale the metric and the conformal factor by any smooth, strictly positive function of M. We would obtain another conformal extension. So in this way, Stripe inherits a smooth conformal structure, which is a class of conformal metrics, where its representative of this conformal structure is a possible boundary metric for a positive conformal extension. So now let M tilde D tilde denote an n+1 Lorentzian manifold, which will be lambda positive Einstein, which I may call a physical manifold. Those are metric manifolds satisfying vacuum equation, where this lowercase lambda is a reduction of the cosmological constant. Now, from the Einstein equations, you obtain that in any conformal extension, the conformal Einstein equation is satisfied. This equation here. From the positivity of the cosmological constant, we find immediately that the conformal structure at the stripe is Riemannian. And additionally, we will say that the conformal extension is geodesic if the gradient of the conformal factor is geodesic. And this is easily seen to be equivalent to the constancy of the norm of its gradient equal to minus lambda. So an important preliminary result is this one. For each representative of the conformal structure at the boundary, there exists a unique geodesic conformal extension inducing that representative at square. Moreover, if we write, have a geodesic conformal extension and we write the conformal metric in Gaussian coordinates, it takes the so-called normal form with respect to gamma, which is this splitting the metric, where G omega is one parameter family of Riemannian n metrics defined on the omega constant leaves, which at omega equals to 0 recovers gamma. So now with these ingredients, I can start talking of the Pfefferman-Graham expansion. In normal form, we perform n+1 splitting of the conformal Einstein equations, which combined with some identities yields these two equations. FG1 are the tangent-tangent components of the conformal Einstein equations. And this is the normal component, and this is the normal tangent component, where A is the Hessian of omega, essentially the second fundamental form. H is the constant, the mean curvature. And this dot stands for the derivative with respect to omega. So let's now assume that the conformal equations in this form are satisfied at omega equals to 0 up to an order k minus 2, where k is lower or higher or equal than 2 by a smooth metric. Then the k minus 2 derivative in omega of fg1 with k different from 0 gives the following recursive relation. This n minus k is a numerical factor multiplying the kth order derivative of the metric equals to a function which depends on previous derivatives up to the k minus 2 order. Okay. So roughly speaking, fg2, from these other two components of the equation, we could do the same thing, and we would get a similar expression for the traces and divergences of the derivatives. So roughly speaking, the Pfefferman-Graham expansion is an asymptotic series expansion, so it's an expansion in omega near omega equals to 0, whose terms are recursively generated by this equation at omega equals to 0 for different values of k. We use the Einstein equation to generate terms in an asymptotic expansion, essentially, and we use a very particular conformality. So let me show the main features. You cannot see here, well, this is in the n odd case, so means n plus 1 is even, okay? Yeah, so maybe it's better because so anybody doesn't lose.
Well, it's his.
Yes. I don't know. Well, okay, sorry. Let's continue. Well, this is the n odd case. Let me change a little bit the notation. I will denote the kth order derivative of the omega at omega equals to 0. Like this is going to be the coefficients of this function. So that the previous equation of d3 is now written in this form. Now, the 0 order is given by the boundary metric and is freely prescribable, meaning that there is no constraint equations for the boundary metric. After we have prescribed this, we have this recursive relation which generates all terms gk with k even strictly lower than n recursively by just a prescription of gamma. The terms gk for k odd are 0, or for k odd strictly lower than n. So now what happens with the k equal to n term? The left-hand side is equal to 0, but also the right-hand side is identically 0. So this means that this equation is consistent with k equal to n. And additionally, this means that the nth order term is prescribable. There is no equation for it, except that the remaining two equations at the two impose this term to be traces of orders. So essentially, by prescribing this G0 and Gn coefficient, the power series expansion can be generated to infinite order with this equation. And this is how the Pfefferman-Graham expansion looks in the n-odd case. Just remember, the spacetime dimension is n+1. Now, the n-even case is quite different. It is the equation has the same form. Some of the properties are the same. So the zero order is prescribed by the boundary metric. It generates all even order terms of lower order lower than k. The odd terms are also zero. But now what happens with the nth order term? The left-hand side vanishes, but the right-hand side doesn't vanish. So this means that one of our initial hypotheses cannot be satisfied. So either this equation, or the conformal equation cannot be, the conformal Einstein equation cannot be satisfied to the n-2 order, or if it is satisfied, it cannot be smoothly satisfied. So we can solve this problem by introducing logarithmic terms. The first logarithmic term is covariantly determined by the boundary metric gamma, and it's the so-called obstruction tensor. One important property of this obstruction tensor is that if it vanishes, it means that no logarithmic terms appear in the expansion. So essentially it means that this equation is consistent to the n-2 order without adding logarithmic terms. And moreover, once we have solved this inconsistency, we can add a smooth power term, which will not affect this equation because of this numerical factor, which is prescribable, except that its trace and divergence are fixed by the boundary metric, and they are in general not zero. So in summary, if we prescribe a zero order term and an nth order term, we can generate a polyhomogeneous expansion recursively with the Einstein equation. This is how the Pfefferman-Graham expansion looks in the n-even case. Is there any questions so far? Okay. Yeah.
So I'm curious about the relationship between this expansion and what you would do if you were just going to solve like the conformal field equations and just post data.
It comes later. It will come
In this case,
yeah.
time.
Yeah. Now with this, I can talk about the asymptotic initial value problem. So in very rough terms, the asymptotic initial value problem at the space I described consists in setting initial data at the hypersurface sigma, which we will a posteriori identify with describe, and we do as usual. With this data and with our equations, supplementing with some conformal gauge fixing condition, we determine a piece of conformally Einstein manifold, where M is the product manifold of sigma times this semi-closed interval of the real line. And when this is done, it happens that in the open interval sigma times the open interval of the real line, the metric G tilde obtained by inversely rescaling the conformal metric is lambda positive Einstein. Okay. In the four-dimensional case, as some of you very well know, this is done with the use of predictive conformal equations. But in the four and higher dimensional cases, this is based on the Pfefferman-Graham products. So for this problem, my asymptotic data are going to be an n-manifold sigma equipped with tensors G0 and Gn with the properties I've discussed before for the coefficients of the expansion. Yep.
Does something actually go wrong with just reducing Helmholtz form if you take n bigger than 3? Could you also just generalize this strategy?
Yeah.
Doing it with perfect brain?
It goes wrong because you don't have enough evolution equations to have well postness in dimensions higher than 4. The equations are hyperbolic. Everything is okay, works perfectly.
Yeah.
But you cannot have well postness.
Why? Because you don't get to give that field.
Well, yeah, yeah, maybe I should have not said this. I don't know. No, the equations are well defined. They are regular, but you don't have well posed in the sense that unique correspondence between data and equation, because you don't have enough evolution equations. So, for instance, in the analytic case, we have that if we prescribe analytic asymptotic data, G bar 0 and G bar n, then the Kerr-Fermat-Graham expansion with G0 and Gn coefficients prescribed at the asymptotic data converges to conformal Einstein and plus one-dimensional measure. And this happens despite the presence of logarithmic terms, and this is what was proven by Chanasami, and this is highly non-trivial. Now, if we want to go beyond the analytic case, this involves the use of the obstruction tensor in a non-trivial way. The thing here is that I have defined the obstruction tensor as a coefficient appearing in the asymptotic expansion of an odd dimensional metric. And it is an operator acting on the boundary metric, which is even dimension. But once I have defined this, it's just a tensor which is covariantly defined. So I can use it I can make it act on whatever metric which doesn't need to be at the boundary of anything. So this is just an operator, well defined for all even dimensional metrics. So for instance, in 4 dimensions, this is the Bach tensor, and has 2 important properties for the asymptotic initial value problem. The first is that it is conformally covariant, and the second is that it vanishes if the metric is conformally Einstein. So Michael Anderson's idea is to use this equation as an evolution equation for n+1 even dimensional spacetime metrics. This equation happens to be a n+1 order hyperbolic differential equation, which moreover propagates the conformal Einstein equation. And this means that the metric satisfying this, which also propagates the conformal Einstein equations, admits a Kerr-Fermat-Graham expansion with n of. This is a bit cumbersome, but you can follow step by step. Everything is it's okay with the dimensions. Okay. Now, since this is an n+1 order hyperbolic differential equation, the initial data are the first n derivatives, but as I have shown before, all the information here is encoded in these 2 coefficients. So in the smooth case, we can have the following well-posted result. So when n is odd, we are given smooth asymptotic data, G bar 0 and G bar n. Then there exists a conformally Einstein n+1 manifold, which has the Fermat-Graham expansion prescribed the coefficients by the initial data. Okay. So in summary, in all even spacetime dimensions or under some analyticity assumptions, G0 and Gn encode the asymptotic degrees of freedom of lambda positive vacuum conformally extendable metrics. Now, if we are given a physical spacetime and tilde, we may want to compute the asymptotic data. Sigma G0, as I said several times, is given by the boundary manifold. Sigma is essentially the topologies given by Scribe, and G0 is the boundary metric. But computing Gn is more difficult because it is coordinate dependent and it is calculated in a very particular geodesic conformal gauge, which is not easy to obtain. And additionally, since the conformal extensions for a given physical space-time are not unique, then rather than one single set of asymptotic data, a physical space-time is uniquely characterized by a whole conformal class of equivalent data. In the case of G0, the conformal class of G0 is easily identifiable as the conformal class of boundary metrics, but the conformal class of Gn is also harder to obtain. So the question we would like to answer is, does Gn admit a geometric coordinate free definition, or at least if it does, in which cases? And does such a definition make the identification of the conformal class Gn simpler? when we have a satisfactory response in the locally conformally satisfied case. So in this case, first let M tilde D tilde meet a conformal extension with locally conformally satisfied. Then the following rescaling of the bitensor contracted twice with the unit norm and to strive. This is also sometimes called the electric part of the rescaled bitensor. Is a smooth tensor, means extends smoothly to strive. Moreover, the asymptotic data satisfies that G0 equals to the boundary metric and Gn is given by this expression. This is the Schouten tensor gamma, which appears only when n equals to 4. But essentially, what this result tells us is that when sky is locally conformally flat, the asymptotic data are equally defined by this geometric definition gamma and d, which is coordinate independent. And from this, it is very easy to obtain that the conformal class of equivalent data characterizing a physical space-time uniquely is given by this class of data, the conformal class of boundary metrics and this conformal class of QT tensors T, set by a different power of the conformal part. So now, with these tools, I can give the characterizations of Kerr-de Sitter and definition of Kerr-de Sitter-like family in arbitrary dimensions. Recall that the Gibbons Kerr-de Sitter metric was written using the Kerr-Schild form. So, to give the asymptotic data of Kerr-de Sitter, we first prove that the Kerr-de Sitter metric admits a locally conformal touchdown. Then the asymptotic data, which are moreover analytic, consists of a locally conformally flat manifold and a QT tensor of this form, where psi KDS is the pullback of the one from K onto a scribe, and it's a conformal king vector field of gamma. So this is exactly the same form with taking these numbers here, this power here, and this number here, that we have obtained in the four-dimensional case, meaning that this data naturally generalizes the data obtained in the four-dimensional case. So we can say that in this sense, at least, Gibbons metric is the higher dimensional generalization of characterization. But moreover, if we substitute this psi KDS by an arbitrary conformal Killing vector field psi of gamma, we would obtain different asymptotic analytic data. So we define the Kerr-de Sitter-like asymptotic data triple sigma gamma d psi. Gamma is locally conformal flat metric, and d psi is the QT tensor for an arbitrary conformal Killing vector field. Now, and of course, the Kerr-de Sitter-like class is the physical space-time characterized by asymptotic data of the form sigma gamma d psi. So we would like now to know how many and which are the families contained in the Kerr-de Sitter-like class. From the equivalence of data I showed previously, we obtain the following result. Two sets of data in the Kerr-de Sitter-like class, sigma gamma d psi, is equivalent to sigma gamma d psi prime. It means equivalent means that it corresponds to the physical space-time. If and only if the defining conformal Killing vector field differs via conformal diffeomorphism of the boundary manifold. This means conformal diffeomorphism is the set of diffeomorphisms of sigma, which acting on the matrix scales the metric by a smooth positive function. Essentially, this is telling us that the classification of the Kerr-de Sitter-like metrics amounts to the classification of equivalence classes of conformal Killing metrics. And there's an interesting consequence. From limits of conformal classes, we will find limits of data, and by well-postness of the asymptotic initial value problem, this is going to be in one-to-one correspondence with the limits of the corresponding metrics. So the space of metrics we will obtain inherits the quotient topology of conformal vectors modulo conformal transformations. So now what we want to do is to work out a detailed description of this quotient space. And to do that, we first select the spherical n metric as representative of the boundary manifold, and we exploit the isomorphism existing between the conformal diffeomorphisms of the n sphere and the Lorentz group in n+2 dimensions, which is represented as matrices in n+2 dimensions. So the quotient space can be equally written as the Lorentz algebra modulo Lorentz transformations, where the group acts under the natural and joint action on its algebra. So with this study, we will obtain explicitly all the Kerr-de Sitter-like terms. And let me show you some of the details of this quotient space, how this works. To parameterize the quotient space, let us first write the conformal vector space of the n sphere in stereographic coordinates. This maps to the following element of the algebra, where A is a column vector of components AA, and B is also column vector of components BA. This omega is an n times n matrix of components omega AB. So now what we want to do is classify the classes of matrices obtained by this, which are also called sometimes adjoint orbits. And to classify them, we need to find a sufficient number of Lorentz invariants. For example, the eigenvalues of the psi, which are equal, they are not equal, but they are equivalent to the real eigenvalues of f squared. We will rather work with those because they are real, nothing else. They are Lorentz invariants. But they are not enough in the sense that they are not in one-to-one corresponding with orbits. So we need to add an additional discrete parameter. There are several possibilities, so we find convenient to use the causal character of the kernel of F. And the idea now is use the information in the causal character of the kernel of F to define an order on the eigenvalues of minus f squared, so that we have a well-behaved global space of parameters for the quotient space. The idea is the joint orbits are in one-to-one correspondence with pairs of with the eigenvalues of minus f squared with the causal character of the kernel of F. We use the information to define an order in this set so that the sorted eigenvalues of minus f squared are in one-to-one correspondence with the adjoint orbits. Okay. So this is how the result looks in the odd case. The details are not really important, just to show you that these quantities are the roots of function, which essentially contain the same information as the eigenvalues of f squared. And this is the rule we find to sort them in such a way that we obtain this global space of parameters for the quotient space. Now, with this parameterization, the class characterizing the Kerr-de Sitter family sits at these values of the parameters, which is remarkable here to see that they are essentially given by the mass and the rotation parameters. Now let us denote by this psi KDS into brackets the region spanned by the Kerr-de Sitter family, which we will obtain by varying the mass and the rotation parameters. This region is open, but not dense in the quotient topology. Fortunately, the complement space of this region can be obtained by either limits of sequences fully contained in the region or an analytic extension of points of the region. And just one more feature of the quotient topology is that it is non-Hausdorff, meaning that sequences in the quotient may have multiple limits.
Do you have examples of that explicitly?
Yeah, I can tell you one. Yeah. I haven't included in the talk, but I can tell you. Now with the n-even case, the things are similar. The eigenvalues change a little bit. The order changes a little bit, but essentially we can obtain a global space of parameters. Again, the class characterizing the Kerr-de Sitter family sits at this value of the parameters, which again is given by the mass and the rotation parameters. Even out again, like here is the region spanned by Kerr-de Sitter family by the mass and the rotation parameters. And in this case, it happens that this region is open and dense in the quotient space. So this means that the complement of this quotient space, all the points are limits of sequences fully contained in cycling-less. Again, in this case, the topology happens to be non-partial. So a summary of what we have done. The space of Kerr-de Sitter-like data, sigma, gamma, psi, are naturally endowed with the quotient topology of Q. We parameterize Q and identify the region spanned by, or the quotient spanned by the data of corresponding to the Kerr-de Sitter family. The whole quotient space can be entirely reconstructed from this region by either limits or analytic extensions. And those limits and analytic extensions are always explicit in terms of the mass and the rotation parameter. Now, the limits or analytic extension of points in the region are in one-to-one correspondence of limit or analytic extensions of the Kerr-de Sitter metric. We calculate explicitly these limits, and the resulting metrics completely fill the Kerr-de Sitter-like class precisely because of this property. And we can classify the Kerr-de Sitter-like class in 8 dimensions. We split it into 3 different families, depending on some properties of the conformal class. And also let me remark that the description through the quotient space here is essential, because the limits and analytic extensions we can see directly from the classification of conformal classes are very easy to guess. But by looking directly at the Gibbon's Kerr-de Sitter metric, there is no way you can imagine that these limits are going to exist. Maybe you're very lucky, but now this is the no. Now I'm not going to give any detail. Just show you that the Kerr-de Sitter-like class of metrics is completely explicit. All the functions are given in this table. So I yeah.
So essentially, metrics are going to infinity.
Yeah.
And will be rotated.
It's a double big rotation.
Yeah, but that does not exist in 1D0.
Probably yes. Probably yes. But you cannot do the same analysis in the lambda equals 0 case, because this is done via asymptotic data. And this is not so simple.
No, I understand, but it should exist. But it's rotated. Kerr-de
Yeah, probably you can just get you can probably find a limit lambda equal to 0. I haven't done the analysis, but yeah.
So the only new one is B in relation to 1 equals 0. It's the only different one in the sense that of the non-unit experience.
Yeah, but the limits when lambda goes to 0, they're probably not so easy to obtain. So I don't really.
No, I understand. It's completely new because you have the parameter and you have lambda.
Yeah.
So then the two you have a competition between two, and so you get a new thing.
Yes.
That's what I'm saying. The only new one is B in relation to the vacuum.
Yeah, probably, yeah.
That I can understand.
That makes sense, yeah. I haven't thought about that, but that's a good remark. So I still have some time to go. If you want to comment something, we can maybe comment about the problem. And then if not, I have some slides prepared describing some of the properties of this family, of this class of metrics. Right? Yeah, so I'm going to then, in the last 5 to 10 minutes, give you some of the properties of the family. Sorry, of the whole class. So if you remember, in the 4-dimensional case, the alignment property singles out a privilege hidden vector field, which is the one satisfying the alignment property. We cannot do that directly in higher dimensions, but we can do something similar. The hidden vector fields of physical manifold can be characterized in terms of the asymptotic data with the so-called Killing initial data equation. So the result is as follows. If we have a physical spacetime characterized by asymptotic data, G0 and Gn, then a necessary condition for this spacetime to admit a Killing vector field is that the following equation is satisfied, where psi is the restriction of the Killing vector field to psi and is a conformal Killing vector field. In 4 dimensions was proved by Paz, and in higher dimensions we proved for the analytic case, this equation is also sufficient condition for the evolving spacetime to admit a Killing vector field. So what it happens that, oh well, yeah, just a remark. We also believe that sufficiency is going to hold in the non-analytic case, but we haven't found proof yet. And what happens with the Kerr-de Sitter-like data is that sigma gamma d psi satisfies the Killing initial data for psi. So in this way, this is singling out a privileged Killing vector field, which in 4 dimensions actually is the one satisfying the alignment property. So we don't have such a thing as alignment property in higher dimensions, but it looks like there is also a privilege from, yeah.
So the need for related to the need for convergence of
Yeah.
Yeah.
Yes. Yeah, it's because it was immediate to prove, and since the Kerr-de Sitter-like class is analytic, so we found an immediate proof using convergence. And let me give you just a couple of more characterizations of the Kerr-de Sitter-like class of metrics. As they are obtained as limits or analytic extensions of Kerr-de Sitter, the Kerr-de Sitter-like metrics all admit a Kerr-Schild decomposition, which the following follow-up condition is always satisfied, meaning the omega squared times this term, it's always the case with omega at this right. So we ask ourselves, is this behavior also characteristic of the Kerr-de Sitter-like class? Well, yes, it happens that it is. So the Kerr-de Sitter-like matrix equals to the Kerr-Schild, all Kerr-Schild metrics which meet this follow-up condition. And a second characterization for that, let me briefly remind you that there's an extension of the Petrov direct classification of the byte tensor to higher dimensions by Collin and others, in which essentially the type 2 is very similar. We say that a metric is type 2 if it admits a multiple file aligned null direction, which was proven by Ortaggio to be equivalent to this condition. If we have a type 2 metric, we can complete the file aligned null direction to a semi-null basis where KL are null, orthogonal to MI, which are space-like unit, and we define the optical matrix in this way. And there is a work of Bernardi, De Freitas, and Harvey Real, and other people from the 2015, in which they explicitly obtain all 5-dimensional metrics, which are lambda vacuum of algebraic type 2 or more special, and have non-degenerate optical metrics. So we ask ourselves if there's a relation with the Kerr-de Sitter-like class of metrics, and it happens that yes, they are exactly the same class of metrics. And just going to finish now, giving you a summary of the seminar. We have given a characterization of n+1 dimension given Kerr-de Sitter in terms of asymptotic data. These data naturally extend the 4-dimensional Carter Kerr-de Sitter. The straightforward generalization of the Kerr-de Sitter data gives rise to the definition of the Kerr-de Sitter-like class, which is endowed with a topological structure, which allows for explicit calculation of all metrics. And each metric has a privileged key in vector field singled out by the asymptotic data. This class also characterizes the Kerr-Schild metrics with an additional call of condition. And in 5 dimensions, the Kerr-de Sitter-like metrics coincides with algebraically special metrics with non-degenerate optical metrics. We believe that this result is going to be possibly extendable to higher dimensions. And we also have reasons to believe that the non-degeneracy of the optical matrix might be substituted by the conformal extendability property. So perhaps this result in 5 dimensions is indicating that algebraically spatial metrics, which are conformally extendable of 5 or higher dimensions, which is not going to be true in 4 dimensions, equals to the Kerr-de Sitter-like class of metrics. And this all.
Do we have questions for Carlos? Yes.
The extension of the Kerr to higher dimension is done by Myers and Perry.
Yeah.
Non-dimension.
No, I haven't. No, I went directly to Gibbons, Kerr-de Sitter.
Because I would say that the Carter did for Kerr what Gibbons thought did for Myers and Perry. Is that correct?
Well, Carter actually in the result by Carter I'm mentioning here is the extension.
That's right. So the extension of the Kerr metric to include positive and actually negative chronological constant was done by Carter.
Yeah.
73.
Yeah.
Now you have the extension of Kerr to higher dimensions, Myers and Perry.
Yeah.
And then the extension of Myers and Perry to include Lambda is Gibbons.
Yeah.
So no reason to not mentioning Myers and Perry.
Yeah, it depends on how you see the connection.
Yeah,
right? I mean, I went from Kerr to Kerr-de Sitter, Carter's Kerr-de Sitter, and from Carter Kerr-de Sitter to higher dimension. By Gibbons, you can do the Kerr, Myers, Perry, and Gibbons.
Yes, okay. So your trajectory, because you wanted to generalize the results in Kerr-de Sitter form.
Yeah, precisely. And I'm interested only in the positive cosmological constant case because it's the one allowing you for a nice asymptotic analysis. It's going to be much harder. There are results, but it's not enough by prescribing data to boundary. You need to do some initial boundary value problem. There is something in higher dimensions by Enciso and one guy from Madrid, but it's probably going to be much more complicated. But it is true that if you take these solutions and you make the cosmological constant negative, or even some of them, you can make them 0. You get different solutions for different values of lambda.
Making statements about uniqueness is going to be harder.
Yeah.
There's no initial value problem. It's
Yeah.
initial value problem.
Yeah, exactly. Yeah.
More questions?
I'm still curious about why the thinking equations break. Do you think that they could be fixed up in higher dimensions by, I don't know, like taking lots of derivatives of the equations that he has, and then instead of posing data for whatever fields he poses data for, posing data for lots of derivatives of the fields? Is that the sort of the issue? The equations that he has don't have enough. We're deep enough in derivatives.
Maybe.
Or is it something more fundamental?
Maybe, but it may happen that in the end you have to go to n plus first order, so you will get something equivalent to this.
Yeah.
Okay. I don't know.
Right, but then it would still be interesting to know, like, is there something fundamentally broken with that setup?
Yeah, essentially, yeah. Yeah, that would be nice to know. But yeah, he says something in a paper I review. He mentions explicit what are the problems with the number of evolutions. Yeah, I can show you that.
Yeah, thank you.
Well, it's going to be a long question, but I was interested in what do we learn from calculating methods in higher dimension? For
Well, what is the interest of these? You mean physically speaking or mathematically speaking? Physically speaking, like high energy people from high energy physics, they've been interested into these kinds of solutions. So this is just adding some mathematical structure to it. If this describes some physical reality, I cannot tell you. So far, it does not. Yeah. Some people, I mean, in mathematics, some people, like, for example, the Pfeffer-Mergelham expansion and all these conformal methods, well, they just like to find applications which are close to physics.
Sometimes studying a high dimensional case teaches you about why things work or don't work in the four-dimensional case. So that's a point that's been made very well in work with Dr. Buzon, for instance. You think that such and such a tale is coming from somewhere, but in fact it's actually just a coincidence.
no, you might be
Yeah.
No, not this world. Some world. No, there's no world here. Now, yeah. In the past, you know.
Are there more questions or comments? Besides the reality of the dimensional.
question in the chat.
There's a question in the chat.
In what?
Yeah.
No, it's just a comment by him. I don't know. It's not a question.
Yes, no. I don't know, like in Kerr, say the extra terms from Schwarzschild give you like frame dragging or stuff like that. And you have like a precise form of the higher dimensional matrix. Could you think of some phenomena or some intuition, like geometrically, of those terms showing up in some dimensions, even though they are real or not? I don't know.
I haven't done this analysis, but I am sure somebody has. To look at the literature.
Okay. Well, if there are no more questions, let's thank Carlos again.
If you enjoyed the video, like and subscribe.